Hello. So in this module, we are going to discuss about the power dissipation in the linear regulator. So as you can go back to our previous modules where we have talked about linear regulator and the types of linear regulators. So a lot of information is already available on our YouTube channel. Now this slide is going to talk about the power dissipation in specifically in the linear regulator. So what you see on your screen is a circuit diagram for the linear regulator where we already know that this is a pass transistor. This is a pass transistor. You have an unregulated supply that is from the battery or from other power source is coming to the circuit, and then you have an output across which you are going to connect a load. That is, let's say this is your load, okay? And that load is receiving the current called load current RL. And now this was your error amplifier. So we have seen how this circuit is working actually. Okay. And this is the resistors which are used to set the feedback into the loop. And this is how it will help to maintain the regulation. So refer back to our previous modules if you are interested in knowing the operation of this circuit. But now the focus here is to understand where is the power dissipation happening here. So linear regulator are known for its maximum power dissipation as compared to its other counterparts such as switching regulators or called as switchers. So switching regulators is not our focus in this particular module. We are talking about linear regulator. So while regulating the output voltage, this is the pass element, whether it is a one single transistor, NPN or PNP, or a combination of the transistors, such as Darlington pair, as we have seen in our previous modules. This pass transistor is always going to be on when you switch on the circuits, right? So this transistor is on, it means it is going to have the current passing through it. For example, this is the input current that is coming through the circuit, and that's the current, let's say, is the collector current essentially, which is actually your current flowing through the load, neglecting the current through the R1 and R2. Okay, so input power in that situation is going to be given by this expression. Power is equal to voltage times the current. So I is this current that is coming to the circuit from the supply, and V in is the input voltage right over here. Now, this power delivered to the load, therefore, is again the power is equal to current into voltage. So we see that the IL is the load current and the V output is your output voltage. So here power is your so the output power in this case is load current multiplied by the output voltage. So this is your load current and this is your output voltage. Now, the power dissipation is simply, again, we can say that the difference between the input power and the output power. So how much power you have at the input of the system and how much power is delivered. And the rest of the power is basically wasted as a heat that is consumed by the circuit, right? So that's the definition. You see that the PD max, maximum power dissipation, is the difference between how much power is received and how much power is delivered to the load. So the remaining power is basically dissipated as a heat by the circuit. And the reason is that while regulating, your pass transistor in the linear regulator is always on. There is one more definition of the power dissipation or the formula. It's a difference between the input and the output voltage. So you have a V in right here, you have a V out right here, and the difference between that two is your VD, let's say VDO, or it's also called as dropout voltage, right? And multiply it with the output current, which is a load current. So you see, while designing a linear regulator or any kind of regulator, this is the main requirement, that the dropout voltage should be as low as possible, which is the difference between input voltage and the output voltage. If it is so, what you see is that your power dissipation is going to be minimized. And that is the requirement of any good regulator with the minimum power dissipation. So we have neglected the power dissipation due to IQ, which is a quiescent current. It is a current when your regulator is not working, it is not active. However, the circuit elements in the regulator still draws this current, and accordingly there is a power component interlinked with that. Okay, so I hope you understood the power dissipation in the linear regulator and how it is related to your dropout voltage, input power, output power, and etc.